Okay, I think we can start. Thank you for everyone for joining. So today we are very happy to announce to you Arjan van der Wel. So he is a colleague from the University of Ghent. And as you might have guessed from his name, he's from the Netherlands. He did his master as well as his PhD at Leiden University. Afterwards, he went to Johns Hopkins in Baltimore, and then he returned to Europe, to Heidelberg, where he worked at the Max Planck Institute for several years. He also got a ERC Consolidator grant, and then he moved then to the University of Ghent, where he's now a full professor. He's specializing in evolution of galaxies on a cosmic timescale, and that was also what his talk of today will be about. So please, Arjan, you have the floor.
Thank you. And good afternoon. Let me first say it's a real pleasure to come out into the world, and I'm making now Leuven the first destination. It's been more than 2 years since I spoke in front of a live audience, other than teaching. So yeah, it's really fun to finally come here. I've been in Ghent for 4 years. I've never been to this institute before, which is almost strange. So before things get awkward, I'm just in time to avoid that awkwardness, I think. So it's great to be here. I've already had great conversations with people this morning. And so today we're going to talk about galaxies. That's not something that you think about every day, not something that you've run into every day. So I don't only want to talk about the research that I have been doing with my group. I also want to tell you something about the state of the field. There's many things that you probably think you know about galaxies, say elliptical galaxies, where they come from and how they evolved. But things have really changed over the past, 2 decades in total, but even the past few years have seen big changes in how we think about how galaxies work, how they evolved and formed. So it's a bit of, in that sense, a lecture too. And I'm going to present a bit of schematic overview of the theory behind galaxy evolution as an introduction. And then I'll show all the empirical evidence, all the bits and pieces. It's way too much to do that completely coherently, so there's going to be gaps in the story, right? So ask me if you want to know. But I'm going to give an overview and then talk about the empirical evidence for what we think about how galaxies work, partially based on my own research and also that of others, of course. So the outline is pretty straightforward. We cannot talk about galaxy evolution without first talking for a few minutes about cosmology. And then there's been 2 main ways, in an empirical sense, to study the evolution of galaxies. One is to take images, right, and count the galaxies, measure their colors, and then infer their cosmological distances and stellar mass content and things like that. From HST imaging, from Hubble Space Telescope imaging, we get information about their structure, even if the universe happens to work in such a way that even at the largest cosmological distances, they can be resolved. They're always 1 arcsecond across, right? The universe is funny that way, the topology of the universe. At some point, galaxies don't get smaller if you move them further away in redshift. Very convenient. You can always resolve them with Hubble Space Telescope. So the imaging is one side of the story, the other side is spectroscopy. Of course, if you want to get into the physics of understanding how galaxies work, their orbital mechanics, orbital dynamics, their stellar population content, you want to take spectra. Of course, spectra of stars is what you're familiar with. So then we're in luck because I specialize in taking spectra of stars in distant galaxies. Of course, not individual stars, all of them together, but still, a stellar spectrum is a stellar spectrum. So I hope that when we get to the second part of this talk, when things get a bit more specialized, it still looks familiar because it's about stellar spectroscopy. Okay, but first things first. So, galaxy formation in a cosmological context. What do I mean by that? So just 3 minutes of cosmology. Of course, we've seen the cosmic microwave background and the fluctuations therein that are the seeds of structure formation, right? These fluctuations in temperature you see in this W map of the sky correspond to density fluctuations, and under their own gravity, these density fluctuations grow and form dark matter halos. Now, one of the beautiful aspects of this observational cosmology field is how well things work, right? If you stick these density fluctuations in a numerical simulation, you can predict what the structure of the universe should look like in the present-day universe. So that prediction is based on this initial condition. The prediction is turns into this distribution of dark matter in a simulated universe with gravity only, right? Only dark matter, gravity only. So initial conditions, prediction. And the spatial distribution of these simulations is statistically indistinguishable from the observed distribution of actual galaxies in the universe. So this is distance, this is a redshift axis, this is an hour angle, so it's basically a slab of the sky. And what you see here are clusters of galaxies and voids, and so every dot here is a galaxy, right, with billions of stars in them. This is the distribution of galaxies in the observed universe with all these filamentary structures. The simulated universe shows exactly the same filamentary structure. This is based on gravity only from these initial conditions, right? And here we see immediately not only how well the cosmological model works, but also that you cannot talk about galaxies without talking about dark matter, without talking about cosmology. So when I was a student, then we hadn't really settled on the cosmological model yet, right? We didn't agree on lambda and the amount of dark matter, universe being open or flat and all these things, which meant that if you look at a distant galaxy, at its flux and its angular size, you didn't know how much luminosity and how many kiloparsec that was. So for every observation we made, we needed to make different plots for different cosmological models about what the luminosity and the size of the galaxy is. So you can't really make progress in the field, right? Everything is degenerate. So then once we agreed on the cosmological model, then the field of galaxy evolution could progress really quickly. That and combined with technological advances in near-infrared imaging. But first things first. So this is, of course, you know this, right? If the total energy content of the universe, based on the CMB observations, we infer that the vast majority of the energy content of the universe in the form of this dark energy. Then of the gravitating matter, most of it is dark matter, and then there's just a sliver of ordinary matter, right? And that all the stars and galaxies and planets are made of. And of course, this is why predicting the structure of the universe based on gravity only kind of works, because everything that does other things than just gravity, right, is just a sliver of the equation. That's why gravity-only simulations are useful and accurate. Okay, so then now we can formulate the question what galaxy evolution is actually about. The key question is, how does this ordinary matter behave inside these dark matter halos? In the early universe, the ordinary matter and the dark matter are just mixed, right? But then the dark matter only feels gravity, the ordinary matter cools and radiates and starts doing all kinds of other things. There's magnetic fields, right? And that's very complex. But this is the key question: how do gas and stars assemble in the centers of dark matter halos? And that's the question I carry with me all the time when I think about my research. If you lose sight of that, you have to ask yourself if you're still doing relevant stuff. So here's what we think we've figured out over the past 20 years. So here's my schematic overview of how we think galaxies form. Of course, how this exactly works depends on the mass of the dark matter halo, and I'll return to that throughout the talk. But we imagine this. There's an early stage where you have a halo of gas and dark matter, and this halo is growing very quickly, right? There's fast cold flows. It's very efficient cooling because the gas is very dense. And this gas falls onto a central proto-galaxy, if you will, where it starts forming stars. These stars, you know way more about this than I do. These stars, right, produce a lot of radiation and winds and feedback, and part of that ends up back in the halo, enriching the halo. So you get the enrichment of the entire halo. Now, this rate of growth is so fast that the galaxy doesn't have time to dynamically settle. Slightly more technical, no, I'm not going to make it slightly more technical, but the orbital time of the galaxy is shorter, is longer than the growth rate. So the thing doesn't have time to find an angular momentum direction, right? There's no stable disk that stays the same, like in the Milky Way galaxy or the planetary system. It grows so fast that its angular momentum direction changes all the time. So we have an irregular galaxy that doubles in mass every few hundred megayears. Okay, but then there comes a moment where this halo has grown so much and the galaxy has grown so much and the growth slows down that the galaxy does have the opportunity to make a disk. Think of the Milky Way disk, right? And then the whole process becomes more steady. There's still significant cooling and growth in terms of stellar mass going on. This feedback not only blows stuff back into the halo, but also cycles back and forth between the disk. It redistributes angular momentum, gives the disk its exponential shape, probably. And in the center of the galaxy, forms a supermassive black hole. It's a very slow process. The growth of this supermassive black hole is not relevant yet for the evolution of the galaxy. It's just there. Just like in the Milky Way, 10 to the 6 solar mass black hole, its energy input into the halo is not very important yet. This is what I call the main stage of galaxy formation. During this period, the galaxies make most of their stars, undergo most of their growth, they're growing up, right? And this is what the Milky Way's current state is. Now, if you're a faster growing galaxy or a more massive galaxy, then at some point, this black hole also gets so massive. One tiny step back. There comes a moment when the galaxy becomes so massive and the gas mass becomes so large that the feedback from the stars no longer manages to keep the gas away from the center. Right? The feedback is not efficient enough. So what happens is the gas starts reaching the center, and then the black hole growth accelerates. The galaxy keeps forming stars, but the black hole starts pumping huge amounts of energy into the halo. This makes for a hot halo, right? First we had halos wherein cold flows could move. And then two things happened. The halo becomes so massive that new gas that falls onto the halo gets shock heated. And then the energy input from the black hole keeps that gas hot. So now the entire ecosystem of the galaxy changes, and we have a hot halo with slow cooling, almost spherical inflow of slow gas accretion onto the galaxy. If it were not for this, and then that prevents further cooling onto the galaxy disk. So now all this galaxy disk can do is use the gas that's already in the disk to form stars, and that stops after 1 gigayear, and it runs out of gas. Right, so at this point there's no dramatic morphological transformations, it's just this, there's no further cooling from the halo onto the disk, so the disk runs out of fuel and stops forming stars, and the galaxy turns red and passive. So then, after that happens, this disk turns red. All that can happen to this galaxy is that it starts eating its neighbors, right? There's tons of satellite galaxies in this very massive halo now, and all that can happen is that these smaller galaxies fall onto the central massive galaxy, further growing the stellar mass, destroying the disk in the process, right? Due to all the different directions of angular momentum of all these other galaxies, and that way you create a massive elliptical. So when you're my age or even older, you've learned that ellipticals were the first galaxies to form. Now I'm telling you they're the last galaxy to form. And this unifies the problem that we had 2 decades ago, where we started to understand that the universe grows hierarchically, small stuff first, big things later, and the observers telling us that the ellipticals are the oldest things and being the first things to form. This story unifies both. Both are true at the same time. These most massive galaxies formed all their stars as the first generations of stars, but the whole thing assembled latest, right? So Very important distinction. The star formation history of the galaxy and the assembly history of the galaxy are, for these massive things, completely different. And that realization unifies that problem that seemed to exist 2 decades ago. Okay, so this is very quick overview of how we view galaxy evolution in theory land. This is what happens in the cosmological hydrodynamical simulations, roughly, right? We don't understand the physics well enough, but mostly this picture has been constructed based on empirical evidence. So, okay, so before I get into this, I was planning to, I'm going to use these little symbols throughout the talk. So whenever I talk about something more specific or technical, there's always moments where we'll hark back to this schematic view of galaxy formation from irregular, mature disk, a disk without star formation because it ran out of gas, and then an elliptical. Okay, so what have we learned from all the imaging surveys that people have done over the past few decades? Well, one of the main things we have learned is the star formation history of the universe as a whole. Now, I think in class you might have seen the classical Maddow-Lilly plot, right? With the star formation density of the universe rising toward redshift 2 and then declining toward redshift 6. That's a very classical figure. I decided to plot that a little bit differently and show the cumulative numbers of stars in the universe normalized to the number of stars that the universe will ever form as a function of the age of the universe. So we're here now. According to the empirical evidence, this is how the stellar mass in the universe, the number of stars in the universe evolved based on measurements at high redshift. And I've used the functional form used by Maddow and Dickinson to extrapolate what happens in the future, right? We know the star formation rate is currently declining because of this the growth rate of halos and galaxies is slowing down for cosmological reasons. If I just extrapolate into infinity, I get this curve. So an interesting observation to make is that by now the universe has made the vast majority of the stars it will ever form. This curve is steepest at between 3 and maybe 8 gig-years, so that's at redshifts 1 and 2, right? That's when the number of stars increased the most steeply. So that corresponds to the peak in the Maddow diagram. That's when the star formation rate was highest. And that's why we call this the high noon of galaxy formation. That's a term coined by Sandy Faber, right? So if you want to know when and how galaxies formed, people like to say that you have to look at this redshift range. People often underestimate the number of stars that form since redshift 1. It doesn't seem like very high redshift anymore these days, but there's many gig-years in between, right? It's about 7 gig-years in between, and almost 40% of the stars that we have today form between redshift 1 and 0. So the spectroscopic survey I'm going to talk about in the second part of my talk takes place here, looking at galaxies at redshift 1 and a little less. Now James Webb, right, is going to study the earliest galaxies in the very first gig-year. And here I'm telling you that it's not a very relevant thing to do, right? That's a bit of a snarky remark, of course, but in terms of stellar mass budget, it's negligible. These first stars and galaxies, we're not talking about when the galaxies formed, as in when all the stars formed. No, it's the seeds of star and galaxy formation. That's what James Webb's going to figure out, and that's important and interesting. But it has nothing to do with understanding why galaxies look the way they do today. Okay, so this is one little nugget of knowledge you can put in your back pocket. If somebody... Now, we don't only know how many stars there are in the universe at any point in cosmic time from the imaging surveys, we also know, that's how we got them in the first place, how they're distributed over galaxies with different masses. So the stellar mass of a galaxy is a fundamental property that we refer to all the time, so that's literally reflects the number of stars in the system. This is at relatively low redshift. Consider this the present day universe. So the mass function of galaxies has this characteristic shape. It's called the Schechter function with a power law here or a double power law and then an exponential cutoff. You might have seen this at some point. The red dot is where the Milky Way sits. That's about the mass of the Milky Way, and it gives you a sense of where it is in this scale. It's near the knee of this mass function. So if you integrate this mass function to see in what kind of galaxy most of the stars live, that's around this knee. So in the present-day universe, most stars live in Milky Way mass galaxies. It's important to know. Now, how does this change with cosmic time? Now, in the other 5 panels, we're going to go to higher and higher redshifts to earlier and earlier times. Right? And what you see is that this shape more or less stays intact. Changes a little bit, a bit steeper here maybe. You know. But at all these different cosmic times, we have the same Schechter type function that describes the population, the mass function. Now this dashed line here is the mass function here for reference. So now we see how the mass function of galaxies evolves, and it turns out to be a very interesting way to evolve, because you think of an evolving galaxy the way I described to you earlier. Galaxies grow in mass, right? They get more and more massive through star formation and merging. Yet that's not reflected here. But if that's what was happening to all the galaxies, then this function would move to the right. Instead, it moves down. Or if we turn around the arrow in time, galaxies grow more numerous, but not more massive, it seems, at first sight. Of course, that's not possible, so somehow there's some complex interplay between how galaxies gain mass and how they evolve in number density. And it turns out to be highly non-trivial to explain this in a lambda CDM universe. I'll illustrate why. So keep in mind, right, the mass function of galaxies evolves up, down with time. This also means, I already told you that in the present-day universe, most stars live in Milky Way mass galaxies, and that's true at all cosmic times, out to at least redshift 3, which may also be counterintuitive. Even 10 gig years ago, most stars in the universe lived in Milky Way mass galaxies. Of course, the Milky Way was not anywhere near Milky Way mass yet, most likely, right? So that's a different statement. Now, this is why it's highly non-trivial that galaxy mass function evolves this way, because this is how dark matter halo mass function evolves. At high redshift, there is a power law and a cutoff, at low redshift as well, but here the evolution is as you expect in a hierarchical universe. Evolution from left to right, all halos become more massive. What's more, the Milky Way halo has a mass of about 10 to the 12th, and there were just as many of those at redshift 2 as at redshift 0. The evolution there is from left to right. This is the hierarchical universe, right? Big things form latest. Yet galaxies don't evolve like this, they evolved up and down in number. And that's why hydrodynamical simulations have to include lots of additional physics to make this happen naturally. If you just put a bunch of gas and let it cool and make it form stars and nothing else, then the galaxy mass function would evolve like that as well. Okay, if I take the two together, the galaxy stellar mass function and the halo mass function, and then take the ratio. So here we have the stellar halo mass ratio. As a function of halo mass, we see the following. A very schematic representation made by Ben Master. There's a peak in that ratio near Milky Way mass halo mass. This is for the present day universe, but the evolution in this thing is, with cosmic time, is surprisingly small. Okay, what do we see here? Why am I showing you this? Several reasons. One is there is a halo mass at which those halos are most efficient in forming their stars, right? That's the Milky Way mass halo. There's a lot of discussion about whether this actually goes down or becomes flat, but it is clear that it steeply rises and then flattens. How? I don't want to go into that. It's difficult to measure the number of stars in very massive halos. Again, this is where the Milky Way is, right at the top. So the numbers here, so 3% of the Milky Way if you take the Milky Way halo mass of 10 to the 12, then 3%, the stellar body of the Milky Way is 3% of the total mass. And given the dark matter and ordinary mass fractions, we also have that for Milky Way type galaxies, 20% of all the ordinary matter of the baryons managed to find itself in stellar form. Right? The rest is gas, mostly outside the galaxy. So if I now draw these, another quick remark that it's worthwhile remembering maybe. This means that most stars reside in Milky Way mass dark matter halos at all redshifts, right? I earlier said, and most stars live in Milky Way mass galaxies in terms of their stellar mass. That's also true for the halo mass. So most stars at all redshifts live in 10 to the 12 solar mass halos. Okay, now I go back to my schematic picture of galaxy formation, and we start to see how this makes sense if you think of these stages as a sequence in halo mass. So for a massive halo, it's a chronological line, right? But if you have galaxies with different halo masses at the same time, you can draw the same sequence. Irregular galaxies grow very fast here, right? Their percentage goes from 1 to 6 real quick. With a little bit of halo mass growth, you grow very fast in stellar mass, faster than the disk can keep up. And here's the main formation phase of the galaxies, where you reach its maximum efficiency. Then for some reason the star formation stops, the galaxy becomes red, and all you can do later on is merge with other pre-existing galaxies, destroying the disk and becoming round. Okay, now so far I've talked about galaxies being points with one property, the stellar mass, maybe halo mass, right? But the next step in our understanding of how things evolve in order to draw my schematic view of galaxy formation is to consider their structural properties. And for that, we need to look at Hubble Space Telescope imaging. And of course, James Webb imaging is around the corner. So it's now old news. The Candle survey, 900 HST orbits, huge thing, made a lot of people very upset, but it also produced beautiful scientific results. In 5 fields in the sky, they took these very deep near-infrared images with the then new VIVC-3 camera. And as I said all the way in the beginning, HST resolves all galaxies in the universe, essentially, because of the funny geometric shape of the universe. So that means that with this survey, we can analyze the structure of more than 100,000 galaxies from redshift 0 to around 3. Right? And that's a really cool thing to do. That's what tells us if galaxies are irregular or normal disks or etc. So just to show you some images of redshift 2 galaxies, fairly massive ones. These are star-forming galaxies, as you can probably just recognize by their structure. And the main point I want to make here is that there's a random selection of Milky Way mass galaxies at redshift 2, so 10 billion years ago, that most of them look like disks. Not all of them, obviously. I don't know what that is. This is some crazy merger. This is very compact. But the majority of these things are disks. These disks have other properties than the Milky Way disk. The star formation rates are 50 times higher. Gas fractions are probably also 50 times higher, right? They're smaller, they're more compact. The whole universe is more dense and more compact. But nonetheless, they're disks. These are in the main stage of formation, right? They're churning out stars at a steady rate. I don't have to take spectroscopic kinematic data to imagine that this is a rotating disk, right? Of course, you can do much more quantitative analysis on making that statement properly, but intuitively, you just see it happening with your own eyes. So now comes the next remark, that most stars live in Milky Way mass galaxies, and those galaxies were disks up to at least redshift 2. Right, so this is a key point, I think, a key result that we've, not in this paper alone, it is the enormous body of work, we've arrived at the point where we say, for most of cosmic time, most stars are born and live in Milky Way mass disks. Crucial thought. That really, brings into focus the key result of decades of work in a way. So here I used the word star forming, and I'm going to contrast that with another type of galaxies that I'm going to call quiescent. And all that means is that star forming means that the mass growth of the galaxy is fast compared to the Hubble time, right? It doubles in mass faster than the Hubble time, and quiescent galaxies don't. Seems artificial, but there's actually a clear separation between the two. I don't want to go into detail here, but this is what it means. Of course, Hubble time changes with redshift. So what is star forming today might be quiescent at the high redshift universe, because your star formation rate ought to be higher. Anyway, it's almost too much detail, almost not necessary for now. So to go back to our schematic picture, most of these Milky Way mass galaxies that are star forming have these extended exponential profiles. And if you're familiar with Sersic profiles, with the Sersic index of 1. Now I'm going to contrast these with the passive galaxies. They look different and the same. They look different. You can see it very easily. If you blink, what's the difference? What's the most striking? Okay, you're not students, but I'm going to ask you. What's the most striking thing? Yeah, these are the same mass, by the way, the same total stellar mass. What's the most striking difference? Concentrated, yes. The central surface brightness is much, much higher. And what's more, they all have it. There's not a single exception here, right? Here we saw that some of them seem to have that, right? Some have high central surface brightness. Others don't. Dust plays a role maybe, but there's rounding errors, right? The order of magnitude here. These, without exception, have a dense center. This informs us about this evolutionary picture of galaxies. Now they're still disks. You might not see that. You need to do some proper modeling to see that. But for some you see a little disky structure, right? And if you do the analysis, you see that a very large fraction of these galaxies, yes, they might have these dense stellar centers, but they're still flat things. They're still disks. Of course, to prove that, you need kinematics, and that's what we're going to do later on at redshift 1. But the radial profiles are different, right? They have a Sersic index of 4. It doesn't mean they're not disks, right? There's, even in galaxy evolution land, there's many people who say, Sersic index 4 must be around spherical galaxy. It's not true. Concentrated light profile is a different kind of quantity than geometric shape and rotation, right? It's two separate directions. Okay, so let's formalize this a bit more. I'm going to measure the sizes of these things. I'm going to literally draw circles and say half of the light of the galaxies is within this radius, the half light radius. Right, so from the Scandals imaging, we see that the quiescent galaxies here in red are consistently smaller than the star-forming galaxies here in blue. That's what's shown in a scatter diagram, as we're all used to. But it's important to realize that it came directly from these images. It's not a subtle thing, right? It really jumps out at you. So we fit these size-mass relations to both of the populations, one shallow, one steep, and I'm going to see how this evolves with redshift. And the next redshift bin, we see many more galaxies because of the pencil beam survey, right? The volume increases at first, and we see the same steep relation, the same flat relation, but a bit offset down, and this behavior continues. To higher and higher redshift, you see the same relations over and over again, just smaller. So it's a very regular evolution in a way, right? At the same time, very dramatic evolution. These galaxies here, they're 1 kiloparsec in half-light radius at the same mass. They're much bigger here. It's a huge change in effective radius, half-light radius. But the slope stays the same. The intrinsic scatter stays the same if you analyze it properly. The slopes change the same, so this is a very powerful constraint on galaxy formation models, right? If you run a simulation and this doesn't happen in your simulation, this regular behavior in the size-mass relation, then there's something wrong. It's a very tight constraint. So now we can draw our schematic galaxies again, and this is a chronological sequence, approximately, right? If you go back in time. We start in the present universe with a massive elliptical. Some 8 gigayears before that, the galaxy was already passive. But between here and there, it grew in mass through merging, right? It also makes you grow in size. I'm not going to go into details there. And then some point before that, it was still star forming. So it was this moment of star formation cessation for this galaxy at redshift 1.5, I imagine, right? This schematic. And that galaxy just evolved along this sequence. Now, this sequence evolves itself, right? So it's a complex thing, but this is schematically what we think might be the evolutionary history of a massive elliptical today. Now, you can immediately argue with this, well, what happens with these massive galaxies? If this is the most massive galaxy today, right? Anyway, don't split hairs here. This is schematic illustrating what we think might be happening. Okay, so I gave you a flavor of what we can learn from imaging, both integrated imaging from the ground and this HST imaging. But really what I've been doing over the past 6 years or so is spectroscopy of galaxies at redshift 1. So Legacy is the name of the survey. It's literally my bread and butter. And what drives the science question that drives the project is, okay, how do these galaxies assemble? And when and why do they stop forming stars? I haven't really talked about that, why that happens, right? I mumbled something about the black hole doing it, but that's just an idea. Now, why do you need spectroscopy for this? Well, it gives us new tools. It gives us tools of, how am I doing on time? Okay, how long is this supposed to last? 5 minutes. Yeah. At this rate? This was the introduction, right? No. I won't keep you here for another hour, I promise. But the spectroscopy gives us new basic tools, right? It gives us access to the stellar population content of the galaxies other than it's old or young, it's blue or red. If you do well, you can get stellar dynamical information out of your spectra through the Doppler broadening, and if you have spatially resolved spectroscopy, you get the rotation curves. Now we don't want to forget about everything we've done before, so we're going to connect the kinematic evolution with the structural evolution. We're going to connect the stellar populations with the gas and the star formation story. I obviously don't have time, and also you're not the audience to go into great detail here, so I'm just going to describe briefly the survey and then pick some highlights of what we've done over the past few years. So Legacy is a public spectroscopic survey at ESO with the VLT. It's a big time allocation. It's actually quite old now, even though it was the last thing that happened with this VLT VMOS instrument. But we're still going strong, and the final data release was last year. So now we're in the middle of the phase where we're writing down the key papers based on the full data set for the first time. Now that's not very interesting to you. What is interesting is this redshift range. It's relatively modest, but if you remember from the beginning, lots of stars formed in the intervening time. Now what I call singular noise and high resolution is singular noise of 20 and a resolution of 4,000 or 5,000. Right? If you're a stellar spectroscopist, you're like, pfft. But these galaxies are magnitude 22, right? That's why it takes 20 hours to collect a spectrum of singular noise 20. Now singular noise 20 is good enough for most purposes because the stellar population models aren't better anyway. Right? The systematic errors then dominate if you go beyond redshift, and singular noise of 40. Also, resolution of 4,000 or 5,000 is enough because all the sharp spectral features of the individual stars are broadened by movements within the galaxy to 10, 20, 30 kilometers per second in the best of scenarios, and often hundreds. Right? So there's no point in taking a higher resolution galaxy spectrum. It's just a waste of singular noise. Okay, so the sample looks like this. As I said, it's a redshift 0.6 to 1. The sample starts at around Milky Way mass and then probes the higher mass end. We have a very clean selection function, so we understand our completeness and volume corrections, which is rare for an extragalactic spectroscopic survey, which usually is we're going to look at whatever we can look at and worry about it later, and then they don't. Right? I think the stellar surveys generally will do a much better job in understanding the selection function and how the biases in the sample affect the conclusions. And we took great care in making sure that that doesn't happen. So here I'm combining all the, or several thousand of these spectra, and I'm just color coding them by the strength of the H gamma absorption index, so it's an H proxy. Right, there's galaxies with strong H gamma absorption, colored in blue, and weak in red. So here we see sort of the young to old sequence of galaxies. This is only to illustrate that we see tons of absorption features in the stellar continuum spectra of these galaxies. The emission lines have been removed via model. I'll get back to that in a minute. Yeah, just to show that even for the young galaxies, for which it's often considered impossible to get metallicity-related features in the spectrum, we do get them. Now, to get an actual metallicity out of that is proved a nightmare, but that's a story for a different day. So let's take a somewhat more detailed look at some of the spectra. So in black is the actual spectrum of a so-called post-starburst galaxy. This is a galaxy that suddenly stopped forming stars 500 megayears ago, and then leaves you with basically an A-star dominated spectrum. The O and B stars are mostly gone, but the A stars are still alive and dominate the entire light output of the galaxy. We have these very strong Balmer lines. So to illustrate what the observations are like, here's an HST image. It's long slit spectroscopy for these galaxies, so we collect basically the integrated light of the entire galaxy with some spatial resolution along the slit. That's sort of the situation you have to imagine when you think of these spectra. So we can build stellar population models that reflect that show this reproduce the spectrum very well, very accurately. And you see that all these wiggles correspond to actual absorption features. But the interpretation of these models is challenging. So a much older elliptical galaxy, even in the earlier universe, might have this spectrum. There's now two different models shown. One fits better than the other. That's because the first one is based on empirical templates, and the other one is based on theoretical templates. You see there's something to be learned. One of the nice things about spectra like these is that in the present-day universe, there are no galaxies of this age and metallicity, right? They're all old, and much older. So this is a look at the stellar population we don't have in the present-day universe, and lo and behold, the theoretical models don't fit very well, so there's something to be learned about stellar population theory here. So as I said, we also have the absorption line spectra for the star-forming galaxies, and they look different, of course. You see the A and B stars, you have Balmer recombination lines, and our modeling disentangles the two, and for that you need some spectral resolution, because as you know better than me, the absorption lines are very wide of these stars because of stellar rotation, etc. And the Balmer lines don't have that broadening. And that's how we can distinguish them. So just to sketch what the situation was like before Legacy, in the decades before Legacy, a bunch of us collected stellar velocity dispersions. I forgot to mention that, right? The other key measurement that we get for every spectrum is the stellar velocity dispersion and the gas velocity dispersion, the Doppler broadening of the entire galaxy. At this point, we don't know if it's a rotating disk that causes a broadening in the integrated spectrum or true random motions like you see in an elliptical. So in my PhD thesis and other people, we painstakingly collected smaller samples of massive ellipticals with stellar velocity dispersions of 200 kilometers per second, up to a few hundred. Only Anna Galazzi took the trouble of analyzing the stellar populations of these galaxies for just 60 of them. And of course, this was a big gap in our knowledge of galaxies and redshift beyond the present-day universe. So that's where Legacy comes in and makes a sample 50 times bigger, samples much bigger part of parameter space. For you guys, that's not so interesting, but of course, for Galaxy people, they're like, yeah, wow, this is cool, and this is a big deal. Okay, so these spectra serve two purposes, as I mentioned. We do stellar populations, right? Ages, star formation histories, metallicities, and we do stellar kinematics. So a quick look at the stellar populations. I don't know if you do this in stellar land, but we like to summarize our spectrum at first by looking at the D4000 break and H delta feature, both being age sensitive and sensitive to the shape of the star formation history if you look at an ensemble of stars. So old galaxies have strong breaks and weak H delta absorption. So the first thing we did, one of the first science papers we wrote, is we compared this diagram with Sloan. This figure in 2003 made Guinevere Kaufman even more famous than she already was. Right? She really put on the map how you utilize integrated spectra of galaxies in a properly scientific manner. So that's without even thinking, that's the first thing we did too. So for Sloan, you see the distribution for present-day galaxies, right? There's a mass-matched sample for legacy and SDSS, so massive galaxies. So in the present-day universe, we see that the massive galaxies are basically all old, with a tail of young galaxies. And we go to redshift 0.6 to 1, and you see that the whole thing moves up. Well, the universe is younger, so the galaxies are younger, but also there's 2 peaks now. These are the galaxies that are still in the middle of their main formation stage. So massive galaxies today, they're basically done. They're petering out. Massive galaxies at redshift 1, half of them were still in their main formation phase. The other half was being dead and passive already. So at redshift 1, about 50% of the massive galaxies are in the middle of their main formation phase. And recently we took a look at the TNG simulation. That's one of the most recent, most advanced dynamical simulations of galaxy formation. And we asked the question, does this distribution in this parameter space look the same in the simulation as in the observed universe? And I have to say, they did a remarkably good job. I thought I was going to show that these simulations are completely rubbish, that all our galaxies were way too young or way too old or something, but it was actually surprisingly good. So TNG, we created mock spectra based attaching stellar population, stellar spectra to all their stellar particles, and it shows that same sort of distribution with 2 peaks in roughly the right location. Now there's important things to learn about these small offsets, but I'm not going to bother you with that. You can read this paper if you're interested. So my conclusion was that without trying, right, the simulation was not set up to reproduce this observation because it didn't exist yet, is that they did a remarkably good job in predicting the age distribution of galaxies in the earlier universe. Of course, you don't want to spend 20 hours collecting these spectra and then crudely summarize them in these 2 numbers, D4000 and H delta, right? So what you really want to do is you want to model the entire spectrum. So we tried that pretty early on, but the big assumption we made here, and that made life easy and the results less reliable, is that all stars have solar metallicity. We just did that as a starting point. We knew these are massive galaxies. It's almost impossible to make a massive galaxy that's not somewhere near solar metallicity within a factor 2, right? You cannot have a Milky Way mass galaxy with a tenth solar metallicity. You just can't do it. So that's why we went ahead and do that. And here we combine the light of stars of different ages, in 12 age bins, just a linear combination, trying to figure out how many stars of each age there are, thereby reconstructing the star formation history. So this is obviously a young galaxy, and for most of the history of the universe, there wasn't much, and then most of the stars formed recently. Now we do this for a whole bunch of galaxies, so we have 3 young examples on the left-hand side. You see differences, right, if you look carefully in the spectra, and that reflects itself in differences in the star formation history. And we have 3 old galaxies here, with the absorption line dominated, the metal line dominated spectra, where most of the stars formed in the first few gig years. So we see a very clear contrast between the 2, and that corresponds to the simplified plot I showed earlier. If I now sort the galaxies by their stellar velocity dispersion, which is a proxy of their total mass, you see that the low mass galaxies had low star formation rates in the early universe and are going up now, right? And the massive galaxies show the opposite behavior. Massive galaxies had most of their star formation in the past and little today. So if we now go back to our schematic view of galaxy formation, we see the following for galaxies that are massive at redshift 1. Right, that their main formation phase in the first few gig years, and now they're old and dead, and they only grow through merging. And drawing this picture more to the right, because the present day is here, right? I should have pointed it out earlier. This is where we observe the galaxies at around the age of the universe of 7 gig years. That's the galaxies that took these spectra off. Present day is here. We don't know what happens, but you can speculate that these galaxies, it's all they can do, is grow through merging, losing their disk-type structure, or they don't change at all. These lower mass galaxies, on the other hand, they didn't do much. They were growing quickly in a relative sense, but not in an absolute sense. They doubled quickly in this time, but really in an absolute sense, the star formation rate is peaking only now. And maybe at some point in the future, it will stop forming stars. Right, so galaxies of different masses are on this evolutionary sequence at different locations. Okay, this gets to be too much because it's both somewhat more detailed and we're running out of time. And I do want to show the stellar kinematics. So I mentioned we can quite easily measure the integrated velocity dispersion, but we also have some spatial resolution, right? Here's an HST image overlaid with our legacy slit. So these are the spatial elements, and in each spatial element we get a spectrum. You extract now not only the velocity dispersion at each location, but also the relative velocity relative to the center, right? So the cosmological redshift is taken out. Now we just look at Doppler shifts from the rotation and the broadening from the velocity dispersion, which is in part rotation, beam smeared rotation. If you do radio astronomy, you might know what I mean. So one interesting thing is that the ionized gas that we see in emission lines shows very much the same pattern as the stars. So whenever somebody tells you that the high dispersion in high redshift galaxies is due to some sort of turbulence and feedback of the stars, they're lying. It's just orbital rotation. So one thing we learned from this is that the quiescent galaxies at the redshift of legacy, they rotate much faster than quiescent galaxies in the present day. And this is the piece of smoke, the piece of evidence, smoking gun evidence, that this merging that I described from disks being gradually destroyed after a galaxy stops forming stars, this is the smoking gun evidence. We had size evolution and we had all kinds of indirect shape-based arguments, but this literally shows that at redshift 1, the quiescent galaxies rotate faster than they do at the present day. This is from a present day galaxy survey. The y-axis here is the ratio between the velocity at 5 kiloparsec and the central velocity dispersion. So the rotation at 5 kiloparsec, here about 150, divided by the central velocity dispersion. So this would have a V over sigma of 1. Sorry, I should have explained that, right? And then you see that there's almost a factor 2 difference between the present day universe and the higher redshift universe. Now this was purely a measurement. We didn't correct for the seeing, which is the same side of the galaxy. We didn't correct for slit geometry and all kinds of things. So the next step is to build dynamical models. It's clearly not enough time to explain how this works, but basically you relate the motions you see to a potential in your model. That potential has several components. We have a stellar component and a dark matter component. You can read in the paper if you want to know more, but this is a very rich field. This is actually the origin of astronomy in Ghent, right? Stellar dynamics, then in a manner that's somewhat more detailed and mathematical than this. That's pretty limited by the observations. Very rich field, it goes back to the 80s. So these models have been around for a long time, have a very rich history, and now for the first time we can use them beyond the present day universe. Okay, so what we learned from that, we can now make the same diagnostic diagrams that people have been making for decades for present day galaxies. So here now is the V over sigma again, but now a model quantity. So all the seeing, smearing, and projection effects and everything is being corrected for. And on this axis we have the projected shape. So if the galaxy is flat in projection or round. Now you see a strong correlation. That's because if you have a rotating disk that you see edge on, right, then you're over here. Then you're both flat and you see a lot of V. The same galaxy viewed face on is round and you don't see it rotate. It's just projection. So now we have a model, so we can deproject the V over sigma and we get this. So we see lots of galaxies with a high V over sigma, rotating galaxies, and here a clump of galaxies that don't rotate very fast. Now the color coding here is with the Sersic index. If you remember, these are the concentrated galaxies. associated with the quiescent galaxies, and these are the exponential disk galaxies. And here we go back to something I said 3 hours ago, that many of this difference in Sircik index or central concentration does not necessarily reflect a difference in dynamical structure. Most of the red points here, most of the galaxies with a concentrated light profile, when you think elliptical, they're actually rotating just as fast as the star-forming galaxies. There is a clump of galaxies down here that are round and not rotating, and these are the classical or elliptical galaxies. They already exist at the redshift 1. They're more dominant today. They're slow rotators, if you've ever heard talks about that. Well, in absolute number, it's a minority. Most quiescent galaxies that don't form stars are just as disky in their dynamical structure as the Milky Way. In detail, that statement is false, because if you over sigmas, depends on what age of stars you look at, right? We can give an entire talk about the dynamical structure of the Milky Way, but these quiescent galaxies are rotationally supported oblate systems. And that statement is correct in a quantitative sense. So that's relating back to the shapes of the galaxies. So it's time to wrap up. I hope I've shown you how the field of galaxy formation has evolved over the past 20 years, give you a bit of an idea of the things we've learned and what we're now thinking about. And then from legacy and specifically, it brought a new dimension to the game, because for the first time, we had access to the stellar populations of high redshift galaxies and their stellar kinematics. And that taught us several new things. It confirmed existing theories or ideas, but on a more quantitative footing. And something I didn't really have time to get into, and it's my fault for planning this poorly. Why do galaxies stop forming stars? And that's kind of the biggest deal in the field these days. Right? In my introduction, I described how we think that works, has to do with the black hole, but now I'm out of time and I don't even have time to show any empirical evidence of that. So that's a bit of a logical flaw in my talk. So please ask a question and I'll tell you more for another half hour. But what I've described to you in some detail is that there's a natural way for gas to stop cooling, right? Because the hot halo and the energy input from the black hole, but nothing happens to the galaxy, it just runs out of gas. So what you're then left with is a quiescent galaxy that is a disk. Maybe that evolves away from being a disk later on, but the transition from star-forming to quiescent is not related to any big merger or dramatic change in structure. Now, in the earlier universe, and rarely in the present-day universe, there is a different way too. And that's related to, here the old-fashioned idea of mergers come in again. If you put two gas-rich mergers together, lots of gas flows to the center, and then in a blink of an eye, you create this dense stellar component that is the characteristic of all these quiescent galaxies. And then there might be the original idea of the quasar feedback blowing out huge amounts of material and changing the entire dynamical state of the galaxy, quenching the galaxy semi-instantaneously. That path also exists, but it's rare in the present-day universe. It's rare at redshift 1, even though there's several dozen galaxies like that in legacy. And in the earlier universe, that's probably the only way to make quiescent galaxies, because there wasn't time to make a hot halo and for a galaxy to run out of gas. Because if that takes a gigayear is not much in the present-day universe, but it's a lot at redshift 3. Right? It's half the age of the universe, almost. So there is no time for this gradual decline in star formation. There you have to do something dramatic. You have to blow out all the gas, stop the star formation via a feedback episode. So that's the part of the talk I didn't get to show, and that's unfortunate, but when I come back next year, I'll do better. Thank you for your attention, and let me know if you have questions.
Thank you, Arjan. That's a very fascinating talk. I'm sure there will be questions, so if you have one, raise your hand, and I will try to move the micro all the way up to you.
Hi, thanks for the talk. It was very nice. I actually have a question on how you model the spectra that you get from galaxies. So what sort of assumptions go into these models? As in, like, for example, one I could think of was what sort of mass function do you assume for the stars in these galaxies? Because in stellar astronomy, we have different mass functions, initial mass functions that we call them, that we assume. And I was hoping you could give us some more insight onto which one is more preferred, for example.
Right, so we have tons of different models, but there's basically no sensitivity to IMF variations in our spectra. Right, the galaxies aren't young enough to see the high mass end, and the low mass end is too faint to have any effect. If you go further to the red, there's more subtle features that you can use to distinguish light from dwarfs and giants, but not in this spectral regime. So all we do is assume a Cabrier IMF, Chabrier, and if we want to compare in the literature with the salpeter, we just change the mass. Now, the stellar populations is a different story, because there we have the choice between Bourgeois-Charlot and FSPS and all the different, the Midas library, right? All these choices that we try them all out. And that's where we get into trouble, because if we want to estimate the stellar metallicity of these galaxies, we get completely different answers depending on the model we choose. There's very fancy Bayesian machinery in making these fits, right? Combining the stellar model spectra to reproduce the spectra, and they reproduce them perfectly. And you get a metallicity of 0.8 solar plus minus 5%. And you run equally fancy machinery with a different underlying model, and you get again a 5% answer, accurate, precise answer, but it's 1.2 times solar, or 2 times solar, right? A huge scatter. And that problem we haven't solved yet, and I'm not sure anymore if we actually will.
Maybe the same question, but posed differently. Are you suffering from the fact that we might have our stellar ages completely wrong? Can you, because for you, aging goes via the redshift, but we do that, of course, quite differently. So let's imagine we have it a factor 10 wrong. Would that affect your spectral fitting?
A factor of 10.
Yes, I tend to be shocking sometimes.
Yeah, a factor of 10 in what exactly? Of the
in age?
Well, I think we can see the difference between a 1 gig-year-old population and a 10 gig-year-old population. I mean, that you can see by eye, right? Or a 100 mega-year-old population. That's obvious. And that's independent of the choice of stellar populations into this model. Now, what can happen is that if you have tons of low metallicity stars that are very old, hiding in your galaxy, they don't produce much light in the spectrum, they don't have strong features, it's hard to exclude that. But here the dynamics come to the rescue, because if you do that, you start breaking just laws of Newton, right? And then the stellar mass, you can put an upper limit on the stellar mass just by measuring the dynamical mass of the galaxy. So there's a limit to how much you can hide in terms of invisible stars. We're actually using that in a project now, putting a limit on the IMF. Say we assume that there cannot be a very massive population of low metallicity stars, because our astrophysical priors tell us that's not the case. So what can you do with the IMF? How many very low mass stars can you add until you start breaking, overproducing the mass of the galaxy? And there's some room, but not as much as some people would like. You know, the Conroy-Van Dokkum IMF is 3 times more massive than Chabrier. That's difficult to accommodate, for example. Does this answer your question, or is it?
Or you can give us an upper limit of how wrong our ages can be.
Yeah, but it's combined with uncertainty IMF, and right. So it's not a very but it's not very one-dimensional either.
Yes, thanks a lot. Very fascinating talk, and a very clear and nice explanation of the build-up of galaxy evolution. Appreciate that. One thing in the general context there, which I wanted to ask, is actually if you see, because this is also sort of a classroom type of thing that we say, that there is a big difference if you sit in a galaxy cluster versus in the field, you know. Spirals live in the field, and then the ellipticals more in, or quiescent galaxies, as I've learned now, I should start to say.
Okay,
in the
let me
cluster.
Interrupt you right there, and then you can
Yeah,
ask your
exactly.
actual
I mean,
question.
do you, both in your survey and globally? Do you see such a difference, or is it?
It's subtle at best. It's also important to realize that 90% of quiescent galaxies are not quiescent because they're in a cluster. Right, and even those that are quiescent sitting in a cluster, they might be quiescent not because they're in a cluster, but because they're quiescent anyway. They were quiescent because before they joined. Now, what you're alluding to is cluster-related physics, like random pressure stripping. You know, getting rid of the interstellar medium of galaxy, and that way you stop their star formation. It happens. And if you look at the 10 to the 15 solar mass cluster, you find a whole bunch of those galaxies. But the mass function of clusters, groups, galaxies is so that to the total budget of stellar mass, they're not very many. And this goes back to my statement that most galaxies live in 10 to the 12 solar mass halos. Right, so also most of the quiescent galaxies live in 10 to the 12 solar mass halos and a bit more.
Right.
And that's, if you do the mass weighting, that's where they are, and they're not cluster galaxies. They're big galaxies, they sit in their own groups, or maybe with several, but it's not gastrophysics like pressure stripping that made them quiescent.
Right.
It's
so
more
it's not
more
it happens, but again, it's not a dominant mode. It's
no.
the
If you go to lower mass, lower stellar masses, then you get more and more galaxies that are affected by their environment in terms of their evolution.
It's very interesting. Then I had a small, in your last slide or the two, where you showed this very nice rotation versus velocity distribution. Yeah, that one. Yeah, it's a very interesting plot, I must say. And do you see, one thing I thought about, do you see, or can you analyze this as a function also of the mass of the system? I mean, the stellar mass?
Yes, absolutely.
Do you see, does it go down with stellar mass, this ratio? I'm sorry if I missed it in some of your slides.
I didn't say it and I went too quick. So I mentioned, yes, there is this group of galaxies that is actually round and non-rotating, right? No matter how you look at these guys, they'll never see them rotate, and those are the most massive quiescent galaxies. But again, there's the numbers game, right? They together they don't account for as much stellar mass as the population as a whole, but they're the most massive galaxies. They sit in the centers of the massive groups and clusters, so they really draw a lot of attention for a good reason, because the physics of clusters is very interesting and important for all kinds of reasons. But as you see, I'm a generalist, right? And say things like most stars live in Milky Way mass halos, and that drives my thinking about these things.
Right. Thanks.
Any more questions?
Thanks. In terms of the subgrid physics that goes into your galaxy evolution models, where do you think are the largest uncertainties? If there are any, or if the subgrid physics is even relevant?
There are plenty, yes. I mean, they're all uncertain, right? That's why I was so surprised that TNG did so well in reproducing an H distribution that roughly looks okay.
That would tell us that some of it at least is not relevant. Some of those uncertainties are not so uncertain because whatever you put in, you get the correct answer.
Well, that's where the small differences we do see come in, because they actually betray a big underlying problem. It's either, but we don't know if it's a stellar population model that's wrong, right? Because we use stellar population models to make the mock spectra. If reality behaves differently, that could explain the difference. Or there's something wrong in the TNG simulation. It seems like a small offset in these spectral indices, but if you want to fix that, you need the galaxies, you need to make them many gig-years older than the simulation and add later bursts of star formation on top, like we think is happening in the real galaxies. So that is a big flaw in the model, but it just didn't look as dramatic. So that's why I only made this very general statement like, oh look, yes, there's also an old and a young group, and it roughly seems to work. So the fact that that's the case doesn't mean that improving the subgrid physics isn't important. Now the biggest uncertainty in those models, I don't know, they don't get the galaxy structures right, and that tells me they don't distribute angular momentum right, and that probably has to do with the stellar winds and the feedback. So you can still write in your proposals that we need to know.
Good for me.
But yeah, cosmic rays are a big thing now. They start to model. Christopher Frommer in Germany is for the first time properly modeling cosmic ray propagation, and now that changes the energetics of the halo. And I describe these halos in a very schematic, there's hot gas, right, and it slowly cools as if it's one homogeneous thing, but it's a mess in these halos. There's little pockets of cold gas there that have no business existing really, but they exist anyway. Now the TNG people start saying they see them in the simulation, so, but they don't know why they exist in the simulation either. And the resolution isn't high enough to properly model that. I don't think there's one thing that you can point at. If you figure that out, then we've solved 90% of the problems. And I mean, I'm an observer in a way, right? So I think 90% of our insights come from observations, and then the simulations are, oh yeah, we see that happening too, because they need to adapt the simulations to reproduce the observed universe. And then you can learn things about, if you see that, that means, because you can track the individual galaxies in the simulation, you can have a conversation between the observation and the simulation. This change in, say, shape from flat to round galaxies in the simulations, that's because 80% of the stars were accreted from other galaxies, the merger history, right? So you can have a dialogue, and people I like talking to best are actually the simulators, not other observers. So because we speak the same language, but I think the information actually comes from the observations, and James Webb will take another step by resolving the structure and of the redshift 4 to 6 galaxies.
Okay, I think I'll keep the last question for myself. So, can you give me your opinion of what you said in your talk, the implications to life in the universe? And the reason why I'm asking is because the number of exoplanets formed must more or less relate to the stars that are formed.
Yep.
And so every Star Wars movie starts with the sentence, in a galaxy far, far away. But from your talk, I understand that it's very unlikely, actually. It's you will far more easily find an exoplanet at very low redshifts than at high redshifts, because simply most of the stars are formed at
Well, it depends what you call far away, right? You're referring to this
exactly
plot, right? So if you go to 45%, so when half the stars formed is about redshift 1.5, 1.4. That's many gig years ago.
okay.
I mean, the earliest simulations of galaxy formation in the 90s formed all the stars here because of cooling catastrophe, right? That was what they thought, the simulators thought was happening. All the stars form early and then all the halos form late. But it's also true that a very significant fraction of all stars formed relatively recently. So I think if I had to draw a planet formation curve here, there being fewer metals at higher redshift, let's say that has something to do with it. But it's kind of have the same shape, roughly. It's maybe a bit delayed. But as I said, most stars here live in relatively massive galaxies, not tiny dwarf things with 100th solar metallicity, right? It's a point I made to Huck earlier this morning. Most stars that existed here early in the universe already lived in Milky Way mass galaxies, and those have to have fairly high metallicity. You just cannot make a Milky Way mass galaxy with even a 10th solar metallicity. It doesn't work. So as soon as you're somewhere near solar, I imagine you can manage to make planets. Maybe it's too simplistic, right? Because the star formation rate was 100 times higher, so the gamma ray burst rate was 100. It's nothing to do with planets, but life on those planets. But
Okay.
things get complicated pretty quickly. But roughly, I would expect that the number of metals evolves in a similar manner, so the number of planets also evolves in a similar manner.
Okay. Okay, thank you very much. I think we can close here. If you want to say hi to Arjan, he will be in the coffee room in the coming hour or something. So yeah, you're all welcome to join us.
Okay.
Let's thank Arjan again. Thank you very much.
Thank you.
There's a difference between being far away in time and far away, but not in you. Go on a flight.